You finally get your hands on a high-end GPU, maybe an RTX 4090. You slot it in, boot it up, and you're ready. But the moment you go online to download a model, you hit a wall. There are thousands of them, different formats, strange acronyms like GUFUF and AWK, and a constant daily flood of new releases. Faced with that chaos, people rely on a simple shortcut. They check their memory capacity, find the absolute largest model that physically fits into it, and hit download. The problem is, size is a terrible proxy for quality. You end up with massive, outdated models that technically fit in your VRAM but spit out hallucinations or generate text at a crawling rate of 2 tokens per second. Finding the actual best model requires balancing specific hidden variables. You have to cross-reference your specific hardware architecture against a model's active parameters, its memory bandwidth constraints, and live benchmark scores. Doing that by hand takes hours of spreadsheet math, pulling data from multiple leaderboards, and estimating overhead to see if a model is viable. Or you can use a single terminal command. A tool called WhichLLM does all of that optimization math instantly, returning a ranked list of the absolute best models your machine can handle. WhichLLM acts as a multi-stage funnel. It starts by actively detecting your specific setup, whether you run an NVIDIA card, an AMD setup, or Apple Silicon, and logs your exact system RAM and compute constraints. Then, it calculates exactly how much space a model will require, and the actual VRAM you need is significantly larger than the size of the file you download. This chart breaks down the true equation. First, you have to load the model's weights. Then you have to reserve a large chunk of memory for the KV cache to handle your conversational context. Finally, you factor in the structural overhead of the framework itself. If that total equation miscalculates by even a few megabytes, the model spills over your GPU memory and into your standard system RAM, creating a massive, grinding bottleneck. By running this strict predictive math up front, the tool completely prevents out-of-memory crashes before a download even begins. But fitting into memory does not guarantee a model is usable. The tool also has to predict how fast it will run, measuring in tokens per second. Local text generation is not really limited by the raw processing power of your graphics card. It is entirely bottlenecked by memory bandwidth, how fast data can physically travel from the VRAM to the processor. This distinction is critical for mixture of experts models. While the total file might hold 80 billion parameters, the model only routes text through a small fraction of them at any given time. The tool calculates your generation speed based exclusively on those active parameters. By checking your bandwidth against those active parameters, it establishes a hard performance floor. Any model that fails to meet a usable generation speed is completely hidden from your results. Now you have a list of models that fit your memory and run at usable speeds. The final step is figuring out which of them is actually the most capable. To do this, the tool queries live APIs from respected independent leaderboards like LiveBench and Artificial Analysis to compile an aggregated quality score. This scatterplot illustrates how the tool handles stale data. Leaderboards age quickly, so the ranking engine applies a confidence dampener that actively demotes older models, preventing them from coasting on outdated benchmark scores. It also targets bad data. If an uploader self-reports an inflated score, or if a tiny fine-tuned fork tries to claim the benchmark of its massive parent model, that data is actively rejected. Because of these filters, the model sitting at the #1 spot is guaranteed to be fast, compatible, and backed by verifiable, modern performance evidence. Once you have your recommendation, you just append the word run to your command. The script instantly downloads the dependencies, pulls the model, and launches an interactive chat session. But WhichLLM is also built for hardware you don't even own yet. It includes a dedicated simulation mode. Input a theoretical or unreleased GPU into the terminal, and the tool mathematically proves exactly which models fit and how fast they run. You can test the exact capabilities of a $2,000 machine before you spend a single dollar. The open-source AI ecosystem has grown so large that access is no longer the bottleneck. We have the models. The real barrier is filtering through the noise to find the exact right tool for your specific machine. WhichLLM takes that chaotic landscape and snaps it into focus, turning the guesswork of local AI into a precise, mathematically sound science.